It is no secret that the transformer model has revolutionized the landscape of machine learning. The uprising gained attention when the transformer model started obliterating the current state of the art on leaderboards for various NLP benchmarks such as Glue, Superglue, Squat, and many more. Fast forward to today, and we're living in one of the most exciting times for AI, where the world has forever changed by GPT-based models or large language models. These models, as we all know, are powered by transformer models. And the race is not over. More and more exciting technologies keep emerging to make transformer models more scalable and efficient. For example, techniques such as fast transformer and flash attention makes the transformers more efficient by diving into the inner workings of the model. Need I say more to convince you that learning about the transformer architecture is one of the best investments you can do right now? In this video, you will be introduced and shown the innermost intricacies of a transformer model in an eye-capturing audio-visual animated tour. So sit back and relax. And I couldn't have done this without the man in Python library allowing me to create these amazing animations. So big shout out there. Let's dive in. First, let's learn about our input. It is a sequence of text. We'll be using the classic example, the cat sat on the mat. The text is broken down to a sequence via a process called tokenization. For simplicity, we are going to do white space tokenization. But transformers build tokenizers using something called byte pair encoding, or BPE. These are smaller subwords automatically found by analyzing a corpus of text that appear to be most common. BPE reigns over white space tokenizing because it can capture out-of-vocabulary words better and have smaller cardinality. Some transformer models have introduced special tokens like CLS, SAP, which serve specialized purposes. For example, SAP denotes the separation between two segments of text. For example, when question answering, you need to feed in a context that contains the answer and a question, so SEP can be used to separate the two. We'll be ignoring these tokens as these were introduced later and weren't part of the original transformer paper. The input processor produces embeddings for the sequence of text. These embeddings have two characteristics. Each token will have a unique embedding based on the characters it has, called token embeddings. Then, tokens in different positions in the sequence would get a different embedding, called the positional embeddings. The token embedding and the positional embedding are added together to get the final embedding. Don't worry if you don't understand fully yet. We will soon dive in. The sequence of text goes through the input processor, which generates an embedding for each token. In our case, we have 6 words, so we get 6 embeddings out. Now let's cement some notation before we continue any further. To understand the transformer architecture, there are 3 key hyperparameters you must understand. Bmax, the batch size. This denotes how many sequences of text you're feeding at once, which is 1 in our example. Tmax is the number of time steps or the context window size. This denotes how many tokens are in a sequence, which is 6 in our example. D is the dimensionality of the embeddings, which is 2 in our example. So the output at this point is a 3-dimensional Bmax by Tmax by D sized tensor. I think the context window size deserves a special mention. This is one of the most crucial levers for modern LLMs to push the boundary on performance. More and more research is happening to discover ways to extend the context window. The longer the context window size, the better the responses of the model will be. For example, GPT-4 can process 32,000 tokens, which is an improvement from GPT-3, which had a 8,000 context window size. Recent methods like flash attention has pushed this to 64K, which is almost the size of an adult novel. A transformer is made of several transformer blocks. Here's what a transformer block looks like. It has 4 layers of computation: self-attention, layer normalization, fully connected layers, and finally another layer normalization. Here, the self-attention layer is the most innovative thing introduced by the transformer. And in fact, that's what gives transformers their great power. Before transformers, we had sequential models like RNNs or LSTMs, which is almost a thing of the past now. They would go through the sequence one time step at a time while maintaining something called a state or memory. The memory helps to leverage past inputs seen by the model to do some computation at the current time step. As you can imagine, this is a lossy scheme. There's no guarantee that they will remember everything needed at the time of prediction. But self-attention layers make remembering long-range dependencies trivial. They have access to any token at any time step. Say you give the transformer the sentence, "The dog ran after the ball, which was red," and ask, what color was the thing the dog ran after? The transformer can attend to the words dog, ball, and then red, see their relationship, and provide the correct answer. LSTMs were not blessed with this privilege, so would struggle to answer something like this. Another benefit is the computational speed. A sequential model needs to execute all n sequential operations to process a sequence of length n, whereas the self-attention layer can process it in O1 steps. But it's important to note that the memory consumption of a self-attention layer is quadratic of n, meaning as the size grows, so does the memory requirement. This is one of the biggest bottlenecks that limits the size of the input of modern transformers can process. There are 2 types of attention: bidirectional attention and causal attention, or sometimes called encoder-style attention and decoder-style attention. Based on the design of the self-attention mechanism, transformers fall under 3 categories: encoder-style, decoder-style, and encoder-decoder style. BERT is an encoder-based transformer. GPT is a decoder-style transformer, whereas in the original transformer architecture is an encoder-decoder style architecture. Encoder-style transformers can attend to tokens in both directions at a given time step. So when processing the second "the", it can attend to "mat" as well as the "cat". Decoders can only attend to the words it has seen in the past. For this transformer, it can attend to "cat" when processing the second "the", but not "mat", as "mat" comes after "the". Finally, encoder-decoder style ones are a combination of the encoder and the decoder, connected via something called cross-attention, where the decoder can attend to the encoder's output sequences. In this video, we will focus on decoder-style transformers, as they're the basis for GPT-based LLMs we see these days. Using the self-attention computation, it produces one output for each token. Don't worry if you don't understand fully what's happening here. We will dig in deeper soon. Just after we compute the self-attention output, we'd add the token embeddings element-wise. These are known as residual connections, and they will help the flow of the gradients when you have very deep neural networks. The layer normalization module takes in this combined input and produces a new output. You probably have heard of batch normalization. Layer normalization does the same thing but on a different axis. Batch normalization computes the mean and the standard deviation for each hidden dimension for each batch and uses it to produce zero mean unit variance outputs. The algorithm computes the approximate global statistics using rolling mean over the training batches. This is used during inference to normalize outputs. Therefore, batch normalization depends on the batch size. This is not ideal as different batch sizes can yield different global statistics. But with layer normalization, you can track the mean and the standard deviation for each input sample, shared across all dimensions, thereby removing the dependency on batch size and leading to better performance. I'll link the necessary papers if you're interested in more details. The feed-forward layer is a simple two-layer neural network. It processes each token independently, or element-wise, and produces a new output. We then repeat the process of adding residuals and passing through a layer normalization module. This gives us the output of a single transformer block. A transformer can have n such blocks stacked on top of each other. The next question is, how does a transformer make predictions? For that, it has a softmax layer on top of the last transformer block. The softmax layer provides the probability distribution over all tokens, and you would pick the token with the maximum probability for a given time step. But how does the softmax layer work when you have a sequence of embeddings? You can simply replicate the same softmax layer weights for each time step and make a prediction. In deep learning frameworks, this is achieved while broadcasting the weights for all time steps. Conceptually, think of it as having a copy for each time step. Now you can make predictions for all the time steps at once. We then compute the losses for all the time steps, average them, and use it for backpropagation and to update weights. Note how our transformer is predicting the next word at each time step. This is the pre-training procedure used by GPT-like models to gain the language understanding. So, how does it work at inference time? At inference, we don't have the full sequence available. If we did, there won't be any need for predictions. We can do a loop where we predict one token at a time. This is known as an autoregressive approach. Specifically, we predict one token, add it back to the input, and predict the next, and keep going until we reach maximum length, or the model outputs the EOS token. EOS is a special token used to denote the end of a sentence. When choosing the next token, there are several strategies to sample tokens at generation. One is greedy sampling, where we pick the one with the highest probability. But this leads to very boring, monotonous outputs. To make things interesting, we can use nucleus sampling, where we sample the word probabilistically according to the probability distribution of softmax. Another method is called beam search, where we predict several time steps ahead and pick the sequence with the highest joint probability. One thing to note is that this is an expensive process. Not only you have to loop through this monolithic structure, having tens or hundreds of billions of parameters. At each step, you have to process more tokens than the previous. So it leads to a compounding effect on the number of flops required in total to complete a sequence of some length. Also note how at each increasing time step, the model has access to more tokens in the self-attention layer, which is the core idea behind causal attention. Remember that causal attention is used by decoder-style transformers. This gives you the full overview of what is the architecture of a transformer model, how does the training work, and how does the inference work. Now let's switch gears and dive into some of the details under the hood. We're going to be talking about two things: how the input embeddings are computed and how the self-attention layer works. The reason we only talk about these two topics is because if you take these out, The transformer is simply a feed-forward network, so there's nothing new about it. First, let's understand how the token embeddings are computed. Remember that the final token embeddings are a function of two types of embeddings. The token embedding is unique to the characters in the token, where the positional embeddings is unique to the position in the sequence. The token embedding is retrieved via a trainable token embedding table as shown here. Each token gets a unique vector. The positional embeddings are a bit tricky. The original transformer model introduced a sinusoidal embedding. The modern transformers have evolved away from this idea and use other techniques such as rotary positional embeddings, which are more generalizable to longer sequences. But let's focus on the original implementation. The idea is that for each embedding dimension, you create a sinusoidal wave. The even positions have a different equation, where the odd positions have another. Both of these are functions of the position or the rank of the token in the sequence. This is what they look like. We have an embedding of dimension 2, so we need 2 such curves. Then you can take the values of each curve at a given timestamp to formulate the positional embeddings for that rank. These sinusoidal curves have some nice properties. The first one, when combined, the vector you get is unique to that position. Secondly, they either gradually increase or decrease as you go along the time axis, so words close together preserve their proximity to each other this way. In other words, the closer the words are, the more similarity they share. Once you have the final token embeddings, we get to the core of the self-attention layer. Self-attention layer forms 3 important outputs of the same shape to the token embeddings we saw. These are called queries, keys, and values. These are the tools the self-attention layer uses to attend to various words during training or inference. Let's learn how these are computed. For the query, you have weights of shape d by d. Now we need to use these query weights to compute a query vector for each position. Remember how we used broadcasting to compute the predictions all at once? We use the same technique here. We repeat the weights across the time and compute the queries for all positions. From a tensor operation perspective, here's what's happening. The input is a Bmax by Tmax by D-sized tensor. Remember, Bmax refers to the batch size and Tmax refers to the number of time steps. We'll transform this so that Tmax is the first dimension. When broadcasted, the weights are of shape Tmax by D by D. When multiplied, we get a Tmax by Bmax by D-sized tensor. Transform this back again and we have a Bmax by Tmax by D-sized tensor, which is identical to the size of the input. Next, we do the same for keys and values. Don't worry if you don't understand the purpose of these. It'll be clear as we go. Note that queries, keys, and values are identical in shape. They only differ in their values. These outputs will define the computation going forward, so let's save them. First thing we need to do is compute an affinity matrix between the queries and keys. You can do this by performing a matrix multiplication between Q and K. The I, jth position in this affinity matrix is the dot product between Qi and Kj. Simple. Note that in the equation, we have a special denominator which is the square root of d. This is something added to stabilize the gradients by avoiding extremely large values in the affinity matrix. Next, we apply softmax along each row. In other words, each row becomes a valid probability distribution. This shows how similar each key token to a given query token. You have most probably seen heat maps like these from transformer papers, and this is where they come from. Put it in a different way, they show how the transformer attend to different words as they're processing various words. Remember, we use causal attention, so our query is not supposed to any future keys, so we mask the upper triangle of our Softmax matrix. In the implementation, you do this by setting those values to a very large negative value. This way, the softmax of these will be close to 0. The next step is, for each row, computing a weighted sum of the value vectors. The weights in this case will be the softmax probability distributions of that row. Note how final values at different rows have different colors to represent different probability distributions of different rows. See how the size of the softmax matrix is T max squared? This is what we mean when we say the memory requirement grows quadratically with T max. Therefore, this restricts how long the sequence of inputs we can fit inside the GPU. With other dimensions like batch dimension or the embedding dimension, the size only grows linearly. However, there are now clever implementations of self-attention that can keep the memory requirement linear by sacrificing some compute. Actually, I lied a bit here. This is not how the transformer model actually computes the self-attention. It uses something called multi-head attention. What we discussed here is single-head attention, but it's very easy to understand this new concept if you already understand single-head attention. What you do is simply do the same computation using sections of your embeddings. You divide your embeddings to some number denoted by number of heads, which is a hyperparameter of the model. Then you carry out the same computations as we discussed for each of these heads. You might be asking, why do this way? Well, there's a few benefits. First, different attention heads can learn different patterns. This is especially valuable when your model has to solve many tasks or understand language complexities. Secondly, you can parallelize the computations between the heads, so that the flop's throughput is higher this way as opposed to a single head attention. You can see that we have a value tensor of same shape as with single head attention, but note that the affinity matrices contain different patterns to the original. So does the value tensor. This is because we're now using different portions of the embeddings to do the computation, as opposed to using full embeddings. Something to keep in mind is that though it looks like we're splitting the current Q, K, and V to multiple parts on the hidden dimension, the transformer paper uses several linear projection layers to generate a new output of that smaller size. This is a small detail I've left out of this animation. So let's replace our single head attention with our newly learned multi-head attention, and voila! We have a fully functioning self-attention layer. Just as we saw earlier, the layer takes in a sequence of embeddings and returns a sequence of hidden outputs. And that concludes our discussion about how the transformer model works. It's nothing to be intimidated by once you understand the details. As we saw earlier, a transformer is made of n blocks. Each block has several layers, specifically a self-attention, a layer normalization, a feed-forward, and another layer normalization layer. The self-attention layer is able to create very powerful representations of language by attending to various words while processing a word at a given position. This allows the self-attention layer to capture various semantics and syntax properties of a language, allowing them to surpass the previous state of the art. I hope you found this journey through the transformer model valuable. I'm hoping this foundational knowledge will help you when you're advancing on papers building on top of the basic transformer model. If you are interested in learning about machine learning concepts, subscribe to my channel, DeepLearning Hero. I will see you soon with another video.